The goal of today's lecture is to prove Hamilton-Cayley's theorem. Let us give its statement. Let T be a linear operator from V to V acting on a finite dimensional complex vector space V. Let f of lambda be the characteristic polynomial of T. Then f evaluated at T is equal to 0, where the 0 is the zero linear transformation. We begin with an example. So let's take A to be the following 2 by 2 matrix: 1, 2, 3, 4. Let's compute f of lambda, the characteristic polynomial. So f of lambda is equal to determinant of A minus lambda I. So we get 1 minus lambda 2, 3, 4 minus lambda. And this is equal to lambda minus 1 times lambda minus 4 minus 6. Or, so this is lambda squared minus 5 lambda, and we have plus 4 minus 6 minus 2. What is the characteristic polynomial evaluated at matrix A? So here we substitute A instead of lambda. And then we get A squared, and this will be the square of a matrix, minus 5 times A, and minus 2. But here we have to convert this to a matrix, so we interpret this as 2 times identity. A squared is the product 1, 2, 3, 4 times 1, 2, 3, 4. And this is equal to 7, 10, 15, 22. And we get, so A squared is 7, 10, 15, 22 minus 5 times A. So that is going to be 5, 10, 15, and 20. And minus 2 times identity, 2, 0, 0, 2. And as we can see here, so the resulting matrix is a zero matrix. And that is the claim of the Hamilton-Cayley's theorem. Let us emphasize the following point. We define the characteristic polynomial in terms of matrices. So this is determinant of A minus lambda I. And when we have a linear operator, it doesn't have a specified matrix. The matrix of a linear operator depends on the choice of a basis. But all these matrices are similar to each other. And we know that similar matrices have equal characteristic polynomials. This means that the characteristic polynomial is not just a feature of an individual matrix, but it's a feature that we can attach to a linear operator. If we perform a change of basis in our vector space and the matrix will change, the characteristic polynomial will not. Let's give a warning. How not to prove Hamilton-Cayley's theorem. So let us show a fake proof of this theorem. F of lambda is the determinant of A minus lambda I. Then f of A is the determinant of A minus A times I. And this is the determinant of a zero matrix, which is equal to 0. This pseudo-proof is a complete fake. We can see that the answer here is a number, whereas in Hamilton-Cayley's theorem, the claim is that the right-hand side of this equality is a zero linear operator. Using the same fake method, we can give a bogus proof of the following bogus result. Let g of lambda be equal to trace of a minus lambda I. Then g evaluated at a is equal to 0. Now, if this were a valid method, we could prove, so to speak, this result in exactly the same way. So if we substitute a instead of lambda, then certainly this will become 0. But let us see, what is g of lambda for this matrix? Here we have that g of lambda is trace of 1 minus lambda, 2, 3, 4 minus lambda. And we see that this is 5 minus 2 lambda. But if we take g evaluated at a, this would be 5 times identity minus 2a. And we can see that this is certainly not equal to a zero matrix. So this result with the trace is completely bogus, so it's absolutely false. But this result with characteristic polynomial is true. Simply, this is not a valid proof of this result. Let us now give a genuine proof of this theorem. By triangulation theorem, T has an invariant flag. Today, for us, it will be convenient to start with a zero space. So we'll introduce the space V0, which is just a zero vector. Then it sits in a one-dimensional space V1, which sits in V2, and so on, which sit in Vn, which is our vector space V. And here we have the dimension of Vk is equal to k, and each subspace is invariant with respect to T. So this means that T acting on Vk will be inside Vk. Let us also choose a basis compatible with this flag. So this will be V1, V2, Vn. So compatible with this flag. Meaning that our space Vk is the span of the first k basis vectors, V1 through Vk. Then the matrix of T in this basis is upper triangular. Let us write down this matrix. So here we will have, on a diagonal, we have D1, D2 up to Dn. We have something above the diagonal, and we have 0 below the diagonal. The columns of this matrix tell us how this linear operator acts on our basis vectors. And in particular, we have that T acting on a vector Vk is equal to, well, the diagonal term will correspond to dk times Vk, plus we have the terms that are above dk. So this will be a linear combination of vectors V1 through Vk minus 1. Let us compute the characteristic polynomial. F of lambda is equal to determinant of Tb minus lambda I, But this matrix is again upper triangular, so it's super easy to compute its determinant. So this will be d1 minus lambda times d2 minus lambda times dn minus lambda. Then we get what is f evaluated at t. So this will be the following product of matrices: d1 times identity minus t times d2 times identity minus t times dn times identity minus t. Now let us look at our flag. So we make the following claim, that dk times identity minus t acting on the space vk brings us to the space vk minus 1. Since the space vk is the span of the first k basis vectors, it is sufficient to show that dk times identity minus t acting on vj brings us to vk minus 1 for all j from 1 to k. We immediately have that dk times identity minus t acting on the space vk minus 1 sits inside vk minus 1. Since vk minus 1 is t invariant. So we have identity operator certainly preserves vk minus 1, and t also preserves vk minus 1. This implies that dk times identity minus t acting on vj sits inside vk minus 1 for j from 1 to k minus 1, because all of these vectors will belong to vk minus 1. Now, to prove this claim, we need to verify that this relation also holds for vk. So we need to compute dk times identity minus t acting on a vector vk. This equals dk times vk, because identity acting on vk gives this vector itself, minus t applied to vk. This equals dk times vk minus, and here we have calculated what is t applied to vk. So here we have dk times vk plus a linear combination of vectors from v1 to vk minus 1. And we see that the terms with vk will cancel, and we see that the result will belong to the space vk minus 1, because we get a linear combination of vectors from v1 to vk minus 1. This proves this claim, that dk times identity minus t acting on the kth space of our flag brings it to k minus first space in our flag. Now, let us act on our vector space with operator f of t. This equals d1 times identity minus t times dot 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 dn minus 1 times identity minus t times dn times identity minus t acting on the space Vn, because Vn is the whole space V. By our claim, when we act on Vn with Dn times identity minus t, we drop into the previous space Vn minus 1. So this tells us that the result of this calculation will be inside the following subspace: d1 times identity minus t times dn minus 1 times identity minus t acting on the space Vn-1. And now, applying our claim again, we see that Dn-1 times identity minus t acting on Vn-1 will bring us into the next subspace Vn-2. And iterating this idea, we will get that this result will be inside d1 times identity minus t acting on the space V1. And applying our claim again, we see that we fall into the space V0, which is a zero subspace. Let us summarize this. So we proved that if we evaluate the characteristic polynomial on our operator t and apply this operator to our vector space, then the result will be in a zero subspace. This means that for all vectors in our vector space, this operator applied to V is giving us a zero vector. So which means that f of t is a zero linear operator. And this completes the proof of the Hamilton-Cayley theorem. We make the following remark, that Hamilton-Cayley theorem is valid over any field, even though we gave the proof over complex numbers, because in our proof we use triangulation and we need complex numbers in order to carry it out. Let us see what happens if we use generic matrices for Hamilton-Cayley theorem. So let us look at 2 by 2 case. So let's take a generic matrix A, B, C, D. Then the characteristic polynomial f of lambda is equal to lambda squared minus trace of A times lambda minus determinant of A, which is lambda squared minus A plus D times lambda, and here we should have a plus, so we get plus AD minus BC. So f of A is going to be ABCD squared minus A plus D times the matrix ABCD and plus AD minus BC times identity matrix. And the claim is that this is equal to a zero matrix. This becomes a system of identities involving polynomials in variables a, b, c, d, and these polynomials will have integer coefficients. Since these identities hold for A, B, C, D in complex numbers, they hold over any field. And although our proof involved the techniques that are valid over complex numbers, the claim of the Hamilton-Cayley theorem is valid in a far more general context. Let us look at Hamilton-Cayley theorem from a different angle. So we know that dimension of the space of n by n matrices is equal to n squared. This tells us that the following set, identity a squared, ... up to a to the n squared, is linearly dependent. Since this set contains n squared plus 1 vectors, and we know that whenever the size of the set exceeds the dimension of the space, this set is automatically linearly dependent. So from here, we get that there exist scalars c0, c1, up to cn squared, not all equal to 0, such that c0 times identity plus c1 times a plus cn squared times a to the n squared is equal to a zero matrix. Consider a polynomial g of lambda, which is equal to c0 plus c1 lambda plus c2 lambda squared plus cn squared lambda to the n squared. Then the previous identity tells us that G evaluated at matrix A is equal to a zero matrix. And we establish the following result, that for any matrix, there exists a non-zero polynomial such that when we evaluate this polynomial on this matrix, we'll get a zero matrix. What we just proved in 2 lines has the same format as the theorem of Hamilton-Cayley. But here we note that the degree of this polynomial is equal to n squared, whereas in Hamilton-Cayley we get a polynomial of degree n. So the theorem of Hamilton-Cayley says the following, that the set I, a squared, and up to a to the power n, not up to a to the n squared, but up to a to the power n, is linearly dependent. And the characteristic polynomial f of lambda provides coefficients of this linear dependency.